Welcome to the Research at City podcast. I'm your host, Elise Badoy, Head of Europe, UK, the Middle East and Africa Equity Research at City. I'm joined today by Martin Wilkie, and we're recording in London. Martin is Head of Cap Goods Research here at City. In this episode, we're really excited to dive into physical AI, and I'm going to dive right in. So, Martin, we've heard a lot about physical AI recently. What does it mean, and how does it differ from the traditional fields of automation and robotics, which we have extensively written about as well?
Yeah, thank you. So, the market for physical AI is getting a lot of press at the moment. It was a big subject at the Consumer Electronics Show in Las Vegas just even earlier this week. And the market refers to any physical process where you are learning from and applying artificial intelligence. So in the same way that AI, of course, is used in text, in large language models, in the physical world, it's where AI meets real world processes. And this is everything from AI being used in quality inspection for paintings on cars, all the way through to factory process, humanoid robots, and autonomous vehicles. So effectively, it's this adoption of AI into the real world. And in the case of what I look at, it's the industrial world. And it's a very broad set of applications where AI starts getting involved in areas, as you mentioned, in things like automation and in robotics. So in terms of the industrial world, this is an evolution of adoption of AI that's already started. So there, of course, like in many industries, AI is used in cases of generative AI. So if we look in things like the service area, a lot of AI has been used already to help service engineers become more efficient. And even in things like agentic AI, where you are making decisions, that's used in things like purchasing and other decision making in factories. But this is really one step further when you're actually getting the physical processes driven by AI. And that's all the way from design and then from autonomy into use as well. And that's where the big disruptions come from. And of course, the big opportunities. In terms of how we think about physical AI, I think we can really split it into two areas. One is around the design process. So if you think about if I'm designing a car or an aircraft wing, or you're really thinking about the very beginning life cycle of an industrial product. And then, of course, all the way through to autonomy in use. So in that first example of the design process, we've seen examples in the past where generative design has used AI to think about improving human decision making on optimizing the design of something. But really, AI in the physical sense really accelerates that and starts coming up with designs that are optimal in ways that perhaps couldn't be done manually, or certainly not in any reasonable timescale. So it really turbocharges that ability to design better industrial processes, better products. And then, of course, and arguably more famously, it's all about autonomy in use. And this is when we start thinking about factories, about warehouses, about transportation, where you have autonomy in use and you're using sensing, vision, and other real world data to come up with this ability to have autonomy in use. So it's really a massive accelerant for the automation and robotics that you've mentioned, and a huge potential driver of productivity once we see this coming into play.
So is this new? There have been investment in the past in digital twins and in the Internet of Things, IoT. Is physical AI something else? We've seen various iterations. So I'm just trying to make sure we understand the pivot here, especially for investors and our listeners today.
So it is additional to those trends, which, as you mentioned, have been really a theme for the sector for several years now. But it's not just slightly incremental, it's massively incremental. I mean, effectively, I think of these digital twins and Internet of Things as the building blocks on which physical AI is then launching from. So effectively, we have this foundation. And one way we can think about this is to have physical AI, you need the information, you need the data. And the industrial internet, or the IoT, that was really putting connectivity onto everything. So many processes, whether it was your car or whether it was a factory process several years ago, was effectively analog. There was a piece of machinery that was operating and producing an output, but there was no digital information as part of that, either for gathering data or for making decisions to actually use the product. And of course, the IoT effectively connected all these devices. And so you're suddenly getting data on everything from processes all the way through to transportation, factories, warehouses, and everything else. So in many, many ways, in the same way that large language model needs huge amounts of text in which to base the decisions on, physical AI needs that same input. It needs data in which to drive its decision making. So the IoT really enables this, because effectively what it's done is to give vast amounts of data into the physical AI process, and therefore it's one of the building blocks. And similarly for digital twins. So for our listeners, a digital twin is effectively a parallel version of a real world process. And so effectively it's your 3D CAD image, if you like, as to what's happening inside a factory, inside a warehouse, whatever else it may be, a transportation system. And it sort of allows you to simulate what's happening in the real world. And effectively, it allows you to tweak processes in a way that you can test it in the digital world before you do it in the real world. And this is not new. This has been happening for some time. The difference here, of course, is that once you have that digital twin, then getting AI to effectively run these simulations to come up with better answers effectively turbocharges the use of those digital twins. And the examples here is that you get real-time learning by physical AI to come up with a better process. If you think about running a warehouse and where do I store the product, what's the optimal route to gathering product from that warehouse before I deliver it to the customer. And in the past, that would have been designed by engineers, and in some ways would have been quite rigid. And of course, in the physical AI world, it learns in real time. It learns that a certain product is more popular than another. It learns that a certain process will be faster than a different process, and therefore it self-optimizes. But of course, to do that, it needs to have all this technology. So we absolutely see this digitization trend that we've seen for a good 10 plus years now really being the foundations, and physical AI is really driving that to the next level. It is worth adding, of course, that there are many, many things that physical AI needs that goes beyond what we've had in large language models. And so there are, of course, constraints in the real world that go beyond just looking at data when we think about the laws of physics, thermodynamics, forces, all these kind of things. And so in many cases, you need not just the software that we've talked about here, but also simulation that understands what the limitations are of running a process, whether that's in transportation or in factories, and integrating these simulation packages with the digital twins, with the Internet of Things, allows you to build this foundation to really drive physical AI. So it's really building on these foundations and massively accelerating the adoption.
So what does this mean for robotics? It seems it's not just humanoids.
No, that's right. And I think humanoids is a very headline-grabbing example, partly because they seem to be so disruptive. And of course, in a sort of sci-fi sense of the word, the humanoid robot is often seen as the sort of natural progression of autonomy and robotics. But in reality, humanoids is just one subset of robotics, and even robotics is one subset of autonomy for physical AI. Remember, we think about autonomy in many things, whether it's transportation, entire systems, not just in robots. But even within robotics, the humanoid form factor is one example. But one thing we've highlighted in the note that we published just at the end of last year is that a lot of what we call task-specific automation is really going to gain investment from here as well, because we've looked at and talked to companies looking at how factories are operated. And in more than 90% of cases, the work done in factories could effectively be done by a single arm. So if you think about a human in a factory today that could be sorting or picking or moving or something like that, even though that person obviously has two arms and two legs, what is needed for that specific task is not necessarily the entire functionality of the human body, and therefore why would you need the entire functionality of a humanoid? So we really see sort of parallel developments here, in where the humanoid will develop in many applications where you genuinely need to replicate the full range of abilities of a human, but in many, many other cases where you just need really a single arm, which, as I mentioned, is very much the case in the vast majority of factories, that we see this task-specific automation really being the most dominant use of physical AI. So we see intelligence getting built onto that. So today, of course, robotic arms are used in many, many areas, whether it's welding or painting or lifting or picking and all these kind of things. But in many cases, these are relatively dumb processes. And of course, adding sensing, adding vision, other sources of data gathering allows that intelligence to be put onto that robotic arm. And so we do see that you get intelligence being brought into many, many other areas of factories as well. It is worth highlighting that in many cases, the humanoid can be bettered for specific applications, particularly if it's load-bearing capabilities. There are other ways to lift heavy loads beyond the humanoid. In the case of picking and sortation, there are some applications that are clearly much faster than the human hand. And this is why we really highlight that you get this adoption of physical AI across many, many different form factors, not just in humanoids. And one example we've given is that in the same way that the horse and cart wasn't replaced by a robotic horse, we show that specialized robotic and automation applications will develop to really optimize those specific tasks. And so you're having form factors that are not necessarily humanoid. Of course, in many applications outside of industry, particularly when we think about service and consumer markets and things like that, the humanoid opportunity is substantial. But we do highlight that inside factories, this task-specific automation is arguably just as important.
And when people talk about cloud versus edge, what does this mean in the case here for physical AI? Will one is likely to dominate?
So this is a big debate that we have with investors. And the reason this has come, I think, to be such a focal point for the debate in this topic is around the investments that have happened so far, because arguably what's happened over the last several years is that everything has moved to the cloud. Particularly when we think about the IoT, the Internet of Things, that has moved data and design decisions to the cloud. And there were huge reasons behind that. And of course, we see this even outside of industrial applications, that moving to the cloud has got huge advantages in scalability, in ease of deployment, in security, in cost. And all these reasons have driven the cloud adoption, not just in enterprise software, but also in industrial vertical software, and in particular on the IoT. But there are limitations with the cloud, and some of these limitations can be latency. So this is literally just time. The data doesn't travel instantly from one place to the other. Of course, cyber concerns. Do you want your highly sensitive factory processes to be adopted or taken outside of your premises? And in many cases linked to that, data sovereignty requirements. In some industries, legally, you have to keep the data inside a certain physical area. And so you can't necessarily have it on the cloud that could be based somewhere else. And so it does matter that we think about this edge versus cloud debate. We do see both really mattering. In industrial term, edge devices are those devices that are at the edge of the network, which is a similar terminology that you have in consumer and other markets. But when we think about industry, edge devices are the industrial hardware components that can gather real world data to be digitized. So this is sensors and switches and things like that, but it's also the items that are then running autonomously, whether it's your car, whether it's a robot. So these edge devices are both gathering data and they're actually in use. And of course, in reality, you need to get both sides of the equation right. You need to get the cost equation right, but you also need to get the latency and data sovereignty question right as well. And so we absolutely see both of these happening. I think a lot of the design process, where arguably latency is less of an issue, is going to remain on the cloud. And so we continue to see a lot of the software movements towards generative design, areas like that remaining very much cloud-based. Arguably, that also spurs adoption. Many of these business models moving towards software as a service, for example, really benefit from the cloud because it gives you massive scale benefits. It reduces the cost, which of course increases the adoption rate. And so on that side, huge amounts of it still will happen on the cloud. But equally, at the edge, there are significant advantages, particularly with latency. One example that is often given here is with an autonomous car. If the autonomous car has a latency issue when it's running, in the real world, i.e. driving down the motorway, you absolutely can't afford to have any latency of a decision between a real world action and the car deciding to stop or start or whatever else it might have to do. And it's the same in factories. Do you really want to have the risk of having any slight slowdown in the data? And for that reason, we see both of these things getting adopted. So we don't think that physical AI is going to suddenly move all to the edge, and that's going to mean that data center investment and things like that are going to somehow slow down or not be needed. We absolutely see both of these happening. And it does mean that you have these two parallel sets of investment on the cloud, which is going to be obviously dominated by large data centers, and then at the edge, where you very much get infrastructure and intelligence built inside industrial facilities, whether that's in warehouses or in factories.
When you look at the success factors, I mean, what will be the critical success factors? How will competitive moats be built?
So we see three key pillars of success for industrial companies here. The ability to create digital twins really matters, because to optimize an industrial process, you have to effectively simulate that before you can think about applying it in the real world. And so really having the understanding of how the real world operates, whether that's the layout of the factory, whether it's your transportation network, whether it's the road network, or whatever else it might be, you need to have information in all of that. So in the same way, the large language models need massive volumes of text of which to learn from, industrial AI needs industrial data. And this really falls into two camps. You've got real world data directly from intelligent devices or from asset management software. So this is effectively that you have sensors, you have all sorts of cameras, whatever else it might be, inside factories and warehouses that's gathering information, and that's giving you real world information and visibility about what's happening that you can digitize. And equally, when we think of asset management software, these are effectively the software packages that are running an oil refinery or running another industrial process. And having access to all that data, regardless of how good your model is inside AI, if you don't have that data, then effectively your model is worthless. And so really having access to that data gives you this enormous advantage. And of course, the installed bases of many industrial companies is that they have vast amounts of on-the-ground equipment that is gathering information already. So we absolutely see one of the big critical success factors as being access to this data and having the domain knowledge of understanding what it means. But of course, because the data in one industry can be very different to another industry, and understanding how a utility works, how an oil company works, how a car company works is very, very different. And therefore having that data and the domain know-how really, really matters. In terms of how that's then used and developed from a business model perspective to create these moats, we do see opportunities both in the cloud, as we mentioned, and a lot of that is in design, in training and simulation, and at the edge, which is really around autonomy, quality, and prediction. And while AI is both potentially a disruptor and an accelerant to the adoption, we do think that, again, this data is arguably the biggest part of the moat. And what you are seeing, of course, is this is driving acquisitions, and you're seeing companies that are perhaps wanting to get much more onto the data side of things, making acquisitions in software, or they're making acquisitions in companies that are gathering the information, whether that's in sensing or elsewhere. And so really it's building this moat to have the ability to get the data and to process the data. So we've often said that, even for software, the industrial install base and the domain expertise becomes the biggest part of the moat. And we very much think that this continuation of ensuring that you understand the data and you understand the application of that data is really going to give companies the ability to create what I think can be very, very disruptive processes in physical AI.
And then finally, Martin, many regions of the world have been in industrial recession. When do we see this investment actually happening?
So we are, I think, at the very beginning of this journey, and that's partly driven by the technology. So we're just at the beginning of the technology becoming available. But then, as you say, we've been in an industrial recession. So part of this is also that the industrial cycle has arguably been sort of against us for really the last sort of 2 or 3 years. So we have seen some of this being adopted already. So if we look back about sort of 5 or so years, you were beginning to see already some very small cases of AI being used in manufacturing, and that was typically predictive maintenance. So this was recognizing certain patterns, that if there was a certain vibration or noise or whatever else it might be, the AI could recognize that this was predictive that an engine was about to break down or something like that. So we've begun to see small applications like that already. We're now beginning to see some of those areas moving across into things like quality control. And so, many car companies now are using AI already to detect whether the paint finish on the car is at an acceptable level. And typically, the sort of success rate, if you like, of AI doing that versus the human eye is already better. So we've seen this beginning to get adopted already, but we really, really are at the very beginning of this cycle. And what we highlight is that industrial technology investments are usually pro-cyclical. And what that means is that if I'm a capital allocator inside an industrial company, I typically don't make the investment in a downturn, even if the ROI is favorable on paper, because arguably the ROI is even better if I wait until an upturn, because many of the drivers of physical AI are there all the time. Labor costs, labor availability, supply chain challenges, all these kind of things, but arguably they become even more pertinent when you move into an upcycle because labor costs get even higher, labor availability becomes more challenging. Oftentimes the inflation of raw materials and so forth go up. And of course, your desire then to become even more efficient becomes much greater in an upcycle. So moving into that industrial upcycle, I think is going to really matter. And that's not been where we've been for the last 2 or 3 years. I mean, really sort of post-COVID, we've had an industrial recession for different reasons in different parts of the world. And industrial production has on balance been in a recession from 2023 up until about the middle of 2025. So there is a cyclical part to this that we think is beginning to inflect. But just as importantly, we think that the technology is now becoming available, and we begin to see this happening already. And I think we can already look at some of the use cases as to how this can show itself into the numbers. And we've looked at things like the industrial robot market. When you look at the industrial robot market, most of the third-party forecasts are that this market can be growing at a mid to high single-digit percentage rate, which is already somewhat attractive, but it's not, it's not exponential or anything like that. But one of the things that we show in the note that we published back at the end of last year was if you begin to get industrial robots that can take more and more tasks away from humans, and a lot of that is because there is no available labor, and effectively you are backfilling for the lack of availability of humans, is that these robots, of course, are much more efficient. They can run multiple shifts per day. They can often be more productive. And the adoption of this can really, I think, massively accelerate that adoption and potentially change the growth rate of that industry from being sort of mid to high single digit to potentially being 20% plus CAGR over the next several years. And so we are really at the beginning of that process. And in many cases, we think this can be additive to CapEx budgets for companies over the next few years. In many ways, simply put, you're effectively changing your wage bill into a depreciation bill. You're effectively moving away from running processes by people to running processes through autonomous either software and design or robots and so forth in factories, and this can really be additive to capex growth, and we've shown that we think this can add a mid-single digit percentage to annual capex growth initially, over the next sort of 5 to 10 years. And so this is really giving us, I think, what can be a very, very appealing upcycle in the adoption of physical AI. And of course, it cuts across many, many different areas, whether it's in robotics, whether it's in design simulation. But this is where we see this growth picking up. As I mentioned, it's linked to the capex cycle and the industrial production cycle. And therefore, we still think we are very much at the beginning of this journey.
Martin, thanks so much for this fascinating overview. This episode of Research at Citi was recorded on Friday, January 9th, 2026, and I'm your host, Elise Badoy.
This podcast contains thematic content and is not intended to be investment research, nor does it constitute financial, economic, legal, tax, or accounting advice. This podcast is provided for information purposes only and does not constitute an offer or solicitation to purchase or sell any financial instruments. The contents of this podcast are not based on your individual circumstances and should not be relied upon as an assessment of suitability for you of a particular product, security, or transaction. The information in this podcast is based on generally available information, and although obtained from sources believed by Citi to be reliable, its accuracy and completeness are not guaranteed. Past performance is not a guarantee or indication of future results. This podcast may not be copied or distributed, in whole or in part, without the express written consent of Citi. Copyright 2026 Citigroup Global Markets, Inc. Member SIPC. All rights reserved. Citi and Citi and Arc Design are trademarks and service marks of Citigroup Inc. or its affiliates and are used and registered throughout the world.